Find f dashed x if f of x equals the integral between x squared and 5 of e to the t dt. So looking at this, you've got this mixture of x's and t's, which already makes it tricky and makes it unfamiliar looking. You are looking to differentiate something that's already an integral, so it's already complicated. You certainly don't need to just go in and integrate the thing and then differentiate that. That is definitely not the way to do it. This is all about the fundamental theorem of calculus, which says that if f is continuous on the closed interval between a and b, when I say f, think of f as being f of t. So f of t in this case is e to the t, which is continuous for all t, all real t. For all real t. Okay, so that's a good start. And then that means that the fundamental theorem of calculus is applied. So because that is true, then d over dx, so that's what we're looking to find, the derivative with respect to x of, well, the fundamental theorem of calculus says that the derivative with respect to x of the integral between a and x of f of t dt equals f of x for any x in the open interval between a and b. So this, we do have some work to do to turn our integral into that, or our f of t. The f of t is okay. The problem is the bounds on the integral, the x and the a. So what we have is the integral, or we are looking to find d over dx of the integral between x squared and 5 of e to the power t dt. So the function is fine, f of t, e to the t, no problem. We've got the dt, no problem. The issue is we don't have this x and an a. We sort of have an a, but it's in the wrong place. So that can be fixed quite quickly. A could easily be 5. So if we did our first step, we can say, well, this is d over dx times minus the integral between 5 and x squared. So if we just use a simple rule, if you just multiply by -1, you can switch the limits around. So then we've got Ra of e to the t dt. So that's a good start, but we can't just apply the rule with an x squared. Now this bit's quite complicated. So we need to turn this into an x, or at least certainly just one single variable on its own, not a function of a variable. So what we're going to do is use a u substitution, and we're going to have to think about, well, can we be creative about the way in which we find the derivative with respect to x? So if we let u equal x squared, so that the x squared is the bit that's making this tricky. So we're going to attack that by substituting in for that. So du by dx would be 2x. Okay, so now what we're going to do, we're going to rewrite this derivative with respect to x. We're going to be quite creative about it, and we're going to say, well, the derivative with respect to x, we're going to turn that into the derivative with respect to u times du by dx, which we just found. So if you look at that rearrangement, you can see that that is equivalent to the derivative with respect to x. So that's what we're going to do. We're going to write this as d over du. We'll use our u substitution, put a du by dx in at the end. So now f dashed x, well, it equals, we've got this minus sign that we need to keep. I'm going to pull the minus sign out first, and then I'm going to write my d over dx. So it is minus, and I'm just going to switch these around. So du by dx, which is 2x, times the derivative with respect to u of this integral between 5 and x squared, we just said x squared was u, of e to the t dt. So now you can see this, the whole thing's rewritten. This whole minus the 2x, and then the derivative with respect to u is just the derivative with respect to x, and then the minus sign was there because we switched the limits. So now this equals minus 2x times, now we're using the fundamental theorem of calculus on this bit, so this just becomes f of u, so it just becomes e to the u, times e to the u, which equals minus 2x times e to the, well, u was x squared. And so we can just tidy that up a bit, minus 2x e to the x squared. And that is our final answer. So it is, there's quite a lot of steps, but it does make sense and we are observing the theorem. The main thing to see at the beginning, just to spot, well, this isn't just something that I'm going to look to integrate. If you were to try and integrate a thing and then differentiate back, you would get in a horrible mess. The letters would all be right. It just wouldn't be worth your time. That's not what the question's about.